Hello, Ryan. How much? How's your morning? Um, I haven't even put up my Q&A questions on Piazza yet. So it's kind of hard to do that for me, I guess.
It looks like on the mural board, everyone's putting up like the answer to the dynamic programming. So I'll claim one of these frames and then I'll just kind of put what we were saying earlier. That sound good?
Okay.
Cool.
A feature they could add to the breakout room is to be able to at Phasey from within here.
All right, how's it going here?
We're doing good.
We talked about dynamic programming in the beginning, but but basically it's the idea that the optimal solution is counting on the basic solution to this subproblem, and also that you effectively use I guess what we were going over on Wednesday was that, sorry, Tuesday, was that that you don't have to, that you should effectively remember calculations if you're going to reuse them as well. So you would like have to maybe save them, or so you're not recalculating them all the time, I guess.
Right. So yeah, that's part of the steps in dynamic programming, which I might go through today formally, depending on what kind of questions we get. But is to like figure out what is this data structure we're going to use, right? What are all possible solutions that we could have? In other words, like what are all possible ways we can call this algorithm? And the other day we saw that there were n squared solutions, right? There are n squared ways to combinations of I and j. And so that meant that our data structure that we use to save it is order of n squared, right? So if you're looking for something to discuss, there's a way to update that algorithm to have order of n size storage. So I'll let you discuss this while I check to see how other groups are doing, and then we'll hop in the main room in a couple minutes.
Okay. Anyone have a clue as to how the storage could be reduced from n squared to O of n?
What algorithm was she talking about?
I think we're talking about the greatest increasing subsequence algorithm.
Probably should have come to class on Tuesday.
Alexa, stop.
But everything is written down, so.
Very true.
Right, another group on it was to kind of review some of the stuff with the longest increasing subsequence. And then there's a question about the algorithm environment. So I'll defer that to Piazza and I'll respond there about how to, the tech questions there. So are there any other questions that your groups came up with that you want discussed? Okay, so I'm going to talk with the loop invariant, and I'm going to look with maybe selection sort, which does have nested loops. So I'm going to just offset one of those to a separate function. So we'll have this sort, and we are given an array A. So this is an array of comparable objects. Okay. And who can remind us how selection sort works?
Selection sort is an algorithm that works in n squared time. It basically loops through the entire list with the main comparison piece at the front, and then you have another for loop that looks through everything behind that one and compares it. And if it sees that particular, let's say that first index, that first index or value is A. If A is, and the second one's B. If A is greater than B, then it will swap the positions. Basically, it will pull the least thing all the way to the left, and then it looks at the next subset over, and it pulls the next thing all the way over to the left after the one from earlier, and it keeps doing that all the way to the end. I hope I explained that well enough.
Mm-hmm. So we're going to loop from left to right, and we're going to pull the smallest thing all the way to the left. Okay. So then let's say J equals index of the minimum value in A of I plus 1 to n. Okay, and this is where that second loop is going to be. So we're going to hide that in a function, so we only have to deal with one loop in this analysis right now. Okay, so then we're going to find this, and then if A of J is bigger than, wait, hold on, never mind. I was thinking, I was getting, trying to do bubble sort at the same time. Anyway, yeah. So then we found the smallest thing. And so then we say that we're going to swap A of J and A of I. Okay. And the way this is written, we could be winding up swapping A of I with A of I. So that's just basically a no op. But that's okay. And then I'm going to end while. And return A. Okay. So this is the algorithm that we're going to look at. Now, one thing in the homework, I accidentally wrote to write your algorithm using a for loop. But for the purposes of analyzing the loop invariant, it's a little bit easier if you have it written as a while loop. You can do it as a for loop. The difficulty there is that the for loop inside the those parentheses for, it increments your I. Oh, that reminds me, we need to increment. So you need to be a little bit careful about where your invariant is held true. I plus plus, and while, and return. Okay. And one thing just like for clarity too, when I write algorithms, especially if I write them by hand, I like to put these bars next to things just so I can see what lines up with what. If I just rely on my eyeballing of indenting, sometimes it gets messy. And I'm going to just number these just in case we need to reference them later. Okay. And maybe it's unclear where that 3 is pushing. Okay, so for a loop invariant, I need to define a couple things. I'll say Boolean expressions. Okay, and we need to define 1 is our loop guard, 2 is our precondition, 3 is our post condition. And I'll write these out in words actually. Loop guard G equals precondition P equals post condition Q equals and our loop invariant. Okay, and then we need to prove the 3 things as well. First, we need to prove the initialization, right? That our loop invariant is true at the beginning. Then we need to prove maintenance. That means the loop invariant at the ith time and loop guard being true implies the loop invariant at the I plus first time. And 3 is end. Right, once I reach the end and not G, then I've achieved my goal. Okay.
Is the initialization for the base case?
Mm-hmm. Yeah, so this initialization in terms of like induction, right? These 2 pieces here are like induction. So this is 1 is the base case. 2 is the Li is the inductive assumption. And then Li and loop guard implies L of I plus 1 is the inductive step. Okay. The additional thing of, for inductive proofs, it's always, we prove something for I equals 1 to forever, right? Algorithms terminate, or they should. So we need to prove that what happens at the end. This end is this kind of extra piece that we need. Okay, so now I need to write all these things down right now because I need to kind of think about all of them in order to really understand what is my loop invariant. Okay, and I'm going to walk you through, and actually I'm going to renumber these because oops. I'm going to do the post condition before the precondition. Okay. And so this is just the way I think through things, and hopefully it'll help you think through them too. So the loop guard is always the easiest one to get. So what is our loop guard here? That's why I do this one first.
It's while I is less than n, or less than or equal
Less than
to.
or equal to. I is less than or equal to n. Okay. Now, what does that mean that not my loop guard is?
That would
It's
just mean that the loop guard's false.
Yeah. And so when the loop guard's false, what do I know is true?
N is greater than I.
Yeah, n is strictly greater than I. Right, and sometimes I just write this down, just right with it, just so I know. I have it right there. Okay, precondition, I'm going to come back to that one, as I said. So the post condition, right? This is what I want to be true at the end of this loop. So what is my goal of this while loop?
To sort the array.
Yeah.
Have a sorted array by the end.
So we can say here, A is sorted. Okay. Now for our precondition, what do we need? What do we know is true, right? Immediately before we get into that while loop, right? And so I'll make a little statement here too. Maybe I put right in this line is where Li holds true. Okay, so it's right after we get into that loop invariant. Sorry, that's right after we get into that loop. It's the thing at the top of the loop. So before we go into the loop the first time, what do we know so far?
The array is sorted. Is that important?
It's not sorted though. We're going to end it up with it sorted.
We know that
Oh, sorry, my mind mixed something up.
I is less than or equal to n.
Yes.
And we know that I starts at 1.
Yeah, and actually here L1 is already true. Yeah, so let's not say that we're let's look at we're looking at like before we get into this while loop. Because we could have sent an empty array, in which case I is not less than or equal to n, so we never really get there. So that's kind of like a vacuous kind of statement. Did someone say something while I was talking and I didn't hear properly?
I have a question.
Uh-huh.
How do we know that else of 1 is already true here if we haven't defined what L is yet?
Yeah, that's what we're trying to figure out, right? We know it's true because we need the precondition to prove that L is true, right? In other words, and so I can put a little 1 here the first time, or for whatever your smallest L is.
Yeah, but I mean, I don't really know. I don't understand how we can say that L1 is true when we have no idea what L is yet. Are we just saying that like the I is 1 is going to mean that L is true when we define L?
Yeah, so the initialization means that my precondition, like what I start with before I'm in my loop, has to imply that my loop invariant is true. Right. So what I'm saying in purple is just interpretations of this loop invariant thing. I don't know what these things are yet, but I'm trying to figure out what are these Boolean expressions that make what I want true. Okay. So if we don't know the precondition, we can come back to that one, okay? Now the loop invariant is something that is true each time so this li holds true at the top of this while loop every time I enter this while loop, and it gets me closer and closer to the solution. So what is my loop invariant here?
Our array from 1 to I is sorted.
Okay. Oh, wait, I was doing 1:i before, so I'll do that here. All right, let's roll with that for now. Oh. Okay, we need to make some adjustment though. Okay. So A1 through I is just the first element. Okay, and so the first time I get into it, A sub 1 is, A from 1 to 1 is sorted, right? Okay, that's vacuously true. So I'm already starting out as a precondition being true. Now, let's look at this maintenance step. My proofs. And you can do these proofs in any order that makes sense. So assume a right, okay. Part 2. Right. We're on the ith iteration. Right, and Li holds, and G, which is equal to, which means is true. Holds. So I is less than or equal to n. Okay. Then what I'm going to do is I'm going to look for the index of the minimum of ai through n. So, okay, so then in line 3, j is the minimum of ai through n, the index of, or the argmin, I guess. And then we need to show, and then we swap. Okay. We swap a of I and a of j, and we need to conclude that a1 to I plus 1 is sorted. Okay. Oh, can we do this? What's the problem right now?
We've only sorted up to the index I.
Right. So let's update our loop invariant. And And so we're going to change this to be A1 through I minus 1 is sorted. So then, whoops, okay. We're on the ith iteration, Li holds, okay. Ng holds I is less than or equal to n. Then line 3, j is the index, so nothing changed there. And we need to conclude here that A1 through I sorted. Okay. Have I done that yet? How do I know that A sub j is bigger than A sub I minus 1?
If it were not bigger, then it would have been selected in when we were looking at the loop last time, I guess. Does that make sense?
Okay, so you're telling me that that was a property of my loop before, so we need to keep that in there somehow. So that's telling me that we also need to add that A1 through I minus 1 is sorted, and A I minus 1 is less than or equal to A sub j for all j strictly, I guess, greater than or equal to I. Okay. Yeah. So in other words, A1 through I is sorted, and they're the I minus first minimum elements. Okay. So let me put this maybe over here, the side remark. In other words, A1 through I minus 1 is sorted, and these elements are the I minus 1 smallest elements of A. Okay. Now this happens often, right? So you kind of have somewhere to start. You have some inkling of where you're gonna, what you need, right? We know that we have it sorted, and we're increasing what's sorted. And then when you try to prove things, sometimes you don't have all the properties you need. So then just go back and update your loop invariance. Okay. So now that if I have this, we swap AI and AJ in line 4 by Li, A1 through I minus 1 are less than or equal to each element in L, all right, we'll say I to N. And by definition, AJ is the smaller, or now it's now AI. Is now the smallest element of AI through N. Okay, therefore, A1 through I is sorted, and the elements are all smaller than those in AI plus 1 to N, which means L of I plus 1 holds. Okay. And this maintenance step is probably the hardest one to prove. So initially, right, if we want to look at this initialization, is probably the easiest one to prove. So now that we know what our loop invariant is, right, or we have a pretty good guess as to what our loop invariant is, we probably don't need much more to it. Most of it will come out in this maintenance step. Now, I need the precondition to say that it's initially true, right? Well, maybe I need at least to know what initially means. So my precondition will say I is equal to 1. Okay. And if I is equal to 1, then I need that A is from 1 to I minus 1. Okay, so this is an empty array, is sorted. Okay. And all the elements, okay, A of I minus 1 doesn't exist. So this is vacuously true. So P implies L, I'll say because vacuously true. And I'll say AKA A1 through 0 is defined to be the empty array. That looks a little messy, so I'm going to rewrite this. Okay. So that's that. Now we need all of A to be sorted. So let's see if we can get there from, if our loop invariant is true and our loop guard is not true, we need to show that we've reached the end, right? So let's assume that, so not G implies that N is strictly greater than I, right? And the loop invariant says that A1 through I minus 1 is sorted. A of 1 through, hold on, I think I put this backwards. I minus 1 is sorted. Right, implies that N minus 1 is less than I minus 1. Right, and if I'm A from 1 to I minus 1 is sorted, that also implies that A of 1 through N is sorted by not G, which that was our goal. All right, super, we did it. Are there any questions on those steps that we took or how we thought through that process?
I have a question about the very last part you did there.
Uh-huh.
I don't see how you, how did you get from I minus 1 in the index to just N?
I minus 1 is bigger than N minus, oh, wait, hold on. Yeah, we should have put N there. This is what I wanted to do. There we go. Right, if I is bigger than N, then N is less than or equal to I minus 1. And I could put this here since I and N are integers. They're both indexes or sizes of arrays, yeah. So then if I know that, right, if I know that A1 through I minus 1 is sorted, that means that A1 through N is sorted. because in order for 1 through 50 to be sorted, I need to have 1 through 20 to be sorted, right?
All right, thank you.
All right, any other questions on these steps?
Just to be clear, none of that is a proof of termination, like the end step. You would also need a decrementing function to fully prove the algorithm.
Right, yeah, so this proves partial correctness. Right, so this is partial correctness. So if it terminates, then it is correct. Let's do a proof of termination. All right. What I need to do is I need to define a decrementing function. We'll call it D. Maybe I'll call it F actually, because I might need a few less distances, but from our state space. To, we'll say the natural numbers. So what is it? So for this, so we need a decrementing function is going to be a function, right? To, this is our favorite well-ordered set. Okay, and so we need a function that strictly decreases each time through the loop. So what function do we want to use for this one? I know you know the answer here. What variable first is changing in the loop?
I.
Is it increasing or decreasing?
Increasing.
Right. So I could put minus I is decreasing if I is increasing, but that's going to put me into the negative numbers. So how can I offset this? What number?
N-1.
Yeah, or I can just add n to it. So now we're going to say our state space. So this is right, a given state. Right. And this has all variables, loop information you need. Okay. And so what I need to show each time I reach line 3, I believe, to f of x is strictly less than the last time I was there. And why is this true?
Because n is constant, but I is incremented.
Yeah, and then we can say here, this is true because in between seeing line 3, we have increased I by 1, which implies decreased f of x by 1. Yep. And that's enough for that, yeah. And so now if we have that, if we know A, it terminates, B, it terminates implies it's correct, right? Then we have that it is correct. Shows it terminates. Okay. So you need both of these things to really do a full proof of correctness. So I'll try to get some of this onto the board here. I'm not really good at sticking on the board, I guess. Okay. So, yeah. Then the other question that we had is about the longest increasing subsequence. So maybe, yeah, one of the group members in that group that had a question about it, state exactly what the question is so that we can maybe try to resolve that together.
So I guess I'm just not, if I were probably to see it one more time, I'd probably get the full understanding of it. I think I understand what it's all about, but I couldn't tell it to you, but I can picture it in my head, if that makes sense.
Mm-hmm. Picture the solution or like dynamic programming in general. What
Well, I have the picture of the graph that we were doing the other day, but I'm not entirely sure as to the fullness of why we were doing that, I guess.
Okay. Yeah, let's look at let's take a step back real quick and look at what is dynamic programming and a formal setup of that, okay? And then go into this. So dynamic programming and I'll go steps to take. From recursion to TP solution. Okay, and not every recursive algorithm has a dynamic programming way to do it, right? Or I guess you can always just memorize, but it might not be necessarily faster. But these are the steps. So the first step is to formulate the problem recursively. Okay, and I'm following this off of Jeff Erickson's book. So, and he gives a whole paragraph description of each of these steps, right? And the formulate the problem takes two pieces. And this is to specify the problem. In English. Okay, and I think this is one part where a lot of students who come into algorithms class, you think about a problem and a solution or an algorithm coupled with the problem. But really, there's a problem, right? I have an array and I need it to be sorted, and a solution, how to sort it. right? And there's many answers to how to sort it. So part A here is really just asking you, like, can we just state what is it we really want to solve, right, in English? And this helps us kind of think about it. Part B is to write this recursive formula. Or write the recursive algorithm. Okay, so while this is the problem, this is the solution. Maybe the first, right? So this is kind of like those piecewise defined functions that we were defining the other day, or the recursive version of the solution. Okay, these aren't going to be perfect, which is fine, right? This is all about thinking through it. Now we need to say, now that we have this recursion, right, we have an inkling that it might be there's a dynamic programming way to go about it. Let's try it. So then we're going to build the solution from the bottom up. Okay, we start here, and again, we're going to break this up into pieces. We're going to identify all subproblems. Right, and so there were theta of n squared for LIS, right? So there's n squared ways that we can call this problem. Now that we know how many problems there are, right, we want to kind of organize them in a nice way, right? Let's say organize our problems. Into a data structure. All right, and for LIS, what we have is we have a 2D table. Okay. And we want the data structure that saves all subproblems. Okay. Now, the thing is, we might revise this later and not actually need to solve all subproblems. That's kind of what I was talking with a couple of the groups today about. But just first pass, we want to try for dynamic programming. Let's take, the simplest approach, and we're already going. We know we're going to have, or we have an inkling we're going to have a really good time savings, right? And then we'll worry about the space savings later. Okay. So then, now that I have a data structure, right? Oh, yeah, and we said 2D table, 2D. Maybe I should say table or array. Okay. So now we have a way to store all of our solutions, right? Now we have to identify dependencies. Which problems need to be defined before which other problems? And this is when we were drawing a graph, right? Draw a graph. Right, this node is equal to an element of our 2D array. And I drew a directed graph. So this is equal to, we'll say AB, denoted that A must be done before B. Okay. Then there's find a good evaluation order so that Maybe I'll put this as a diagram. Diagram of dependencies is honored, I'll say. Okay, and then here, I guess we'll put this here. As long as no cycles, we can use topological sort. Okay. And we don't have time to get into more details of topological sort today, but that's the solution that we were looking for the other day when we had this full graph and we're saying, okay, which order? Okay, and a lot of us observed that any one, and the general idea here is start with any node that has no incoming edges. Okay. And as long as there's no cycle, there always is a node with no incoming edges. Okay. Then, okay. A, B, C. Okay. Identify dependencies, good evaluation order. Oh. Analyze space and runtime. Right? Each problem is kind of equivalent. So you basically multiply the number of subproblems times each subproblem. Right? Often, and so sometimes there's a little bit of size of data structure. Times cost of one computation. Okay, it might be that they're not all equivalent, right? So it could be slightly different, but usually, often, it's you basically multiply it because we'll say these are usually constant if subproblem's known. Okay. One of the other cool things that I thought, as a side note, there's an algorithm I worked on, which was a dynamic program, but there was a cycle in our graph, right? And so this means that we could just keep going. But we could prove that if we went through this cycle at most, say, n times, then we found our solution, so that we could change each time through, but there's only a certain number of changes that were allowed. So that was a really fun dynamic program to work on. But the final step is to write down our algorithm. And then I also want to put here, should be number 3. Can we improve? And usually we're going to improve on the space. Okay, and for our LIS, if you want to challenge yourself here, LIS can be improved to use only theta of n space. Okay. So maybe this helps give a little bit of perspective as to why we were looking at this graph of things. I think probably the biggest question is this topological sort. Yeah. But we'll dive into that a little bit more. I'll start with that next time. Okay. Yeah, good questions today, and I will see you next week.
Thank you.
And I have a couple minutes if there's some questions that weren't answered too.
Professor Fazy,
Mm-hmm.
if I would like to contest the grading of one of my homework assignments, who do I talk to? Do I talk to the TA or you?
Yeah, talk with the TA.
Okay, and I should
Yeah,
do
and
that
if you
on
have
his
trouble
office
still,
hours.
you can contact me, or you can CC me when you communicate with him, but he's been handling those.
Okay, thank you.
Yeah.
Quick question about the skyline problem.
Uh-huh.
There's no one output, right? You could have any number of correct outputs so long as the computer could draw it in a Cartesian plane.
Can you give me an example that has two different outputs?
Yes. You could do like a set of XY pairs with each corner being denoted, each corner of the cityscape being an XY pair. Or you could do a set of horizontal lines for each roof. Does that make sense?
Well, okay, so I think in the output should start, okay, the output should start with min x 0, max x 0.
Mm-hmm. Wait.
And design an algorithm that takes buildings and inputs and returns a skyline, where this skyline is a sequence of XY coordinates. So we need a sequence of XY coordinates that starts at the very left and ends at the very right.
Okay. So you can't, okay. Okay.
There is an example that I could think of that you might do, which would certainly still be true. So in general, this is our skyline. We have a couple buildings, whatever they may be. Or you could have buildings hidden inside buildings. But then when you go,
okay,
I'm on the Miro, yeah.
Yeah.
So we're gonna have this is our min x 0. This is our max x 0, and I'm ignoring the indexing for the x's. So just sorry about that, just to make it a little clear. And so, okay. Yeah, so maybe I change the colors here. So I could, and I didn't do this right. Yeah, let me draw one more building in there. Suppose that this one winds up being like this, right? So I would have to do it in this order. So I'd have to go here. Now this is where the question comes in, right? So this point, and I didn't draw that so well, but
yeah, so that point should not be included, correct?
Well, you may or may not.
Okay.
Right, because it's 3 points in a line. You don't need all three of them. But if whatever algorithm you're doing, it's better for you to include that, that's fine too, because it's not incorrect to include it, right? Because it's going to be the same line that we're drawing.
Okay.
So I don't know if that's what you're thinking, but I think.
Yeah, kind of. I guess, and maybe it's just trivial because they're so similar in the end, but I was like stuck on kind of, if you could see that, two different ways of representing it, where this is the roof, just a horizontal line for the roof, versus a XY pair for each corner.
Mm-hmm.
So it'd be like.
Yeah, I think in general, like you can talk about you can actually just give the horizontal lines and you can imply what the vertical lines are.
Okay.
But
I guess that's
asks for the sequence of XY coordinates.
Okay.
Yeah.
So don't imply.
Right.
Okay.
Yeah. Give the coordinates.
Okay. And then, is there a reason that you recommended not to use matrices? On Piazza, I'm just curious.
I think the matrix might be a little more restrictive, right? Like what if like the building is an object and I said it came with 3 values, but it could come with more values, right?
Mhm.
So thinking about it as an array of these building objects is a little more general.
Oh, okay. Okay.
But it's not incorrect if you tell me that's the data structure you're storing it in, it's not incorrect, right?
Okay.
I was just giving what I would do if I were programming it.
Yeah, I guess I was just thinking strictly in like primitive and not thinking of like it's just an object. Okay, cool. Thank you.
Yeah, you're welcome. Does anyone else here have additional questions? Or just hearing our answers? All right, I'll see you.